Okay, so I repeat. I introduce the algebra of symmetric polynomials. Symmetric polynomials in n variables. And it has a basis. I recall the notation. These are the Schur polynomials, which are indexed by Young diagrams, arranging over this set. This means the set of Young diagrams or partitions of length, which is at most n. And the initial definition of this object is the polynomials in n variables. It is a ratio of two determinants. One is this one, and in the denominator you have the van der Monde determinant. And here I use the notation L, which is L1. And by definition, L sub I is lambda sub I plus n minus I. Okay. Next, the algebra of symmetric functions. Algebra of symmetric functions can be introduced as follows. It is a graded algebra. It is a graded algebra. And as a graded algebra, it can be defined as a projective limit in the category of graded algebras. The projective limit of the algebras of symmetric polynomials. And it is also contained, take, say, the base field of rational numbers. These are formal power series in infinitely many variables, which are symmetric with respect to the action of the finitary symmetry group or the complete symmetry group, does not matter. Okay. And in the algebra of symmetric functions, we have a basis of Schur functions. Here, lambda ranges over all partitions, and I identify partitions and Young diagrams. And informally, this is the limit as n goes to infinity of the corresponding Schur symmetric polynomials. How to understand this? This means that this means that if you take the Schur symmetric function and substitute finitely many variables, which can be arbitrary, and the next variables are all equal to 0, then what we get? We get either the Schur polynomial in these x variables. This holds in the case the length does not exceed. Otherwise, you have 0. So this is a very important, this is easy, almost trivial, but it's very important to understand the nature of these Schur symmetric functions. Next, I would like to remind you about the combinatorial formula. Combinatorial formula for the Schur symmetric function. It says the following. So I repeat that this should be viewed as some formal power series in infinitely many variables, and as such, it can be given by the following formula. We have an infinite sum over all tableau of a shape, of a given shape lambda, and to any such tableau, we assign some monomial x sub t, which is defined as follows. I recall that Young tableau, here I mean semi-standard, means the following. We have a shape, the diagram of lambda, we have some shape, and we put some variable. This is a variable which corresponds to this box, 1, 2. So this is the box 1, 2, and there is some maybe, no, sorry, this is a bad notation. Sorry, excuse me. So if this is the variable indexed by the number which is contained in this box. And then by the very definition, we said is the product over all boxes of our diagram. There are finitely many boxes, so we take, and the condition on the numbers which are contained in our Young diagrams is as follows. This number weakly increase along the rows and strictly increase down the columns. Okay, so this is the definition. Okay, so now I would like maybe one more remark. So instead of the variables x1, x2, and so on, we can use any set of variables, which any set of formal variables, say x. For instance, we can, what I would like to say that using any set of formal variables, we can write this. What this means, this is some formal power series, in the variables x, ranging from this set capital X, which I will call the alphabet. So one can think of these small x's as letters from this alphabet. And if you want, so this alphabet can be absolutely arbitrary. Assume it is a countable set, for instance, but even if this is not important, but if you want to deal with the combinatorial formula, to use the combinatorial formula we have to assume additionally that our alphabet is totally ordered. Then the definition of the combinatorial formula is exactly the same, because what we need to understand what means that we fill the boxes by variables, and the entries should satisfy our condition to be strictly increasing, weakly increasing in this direction, and strictly increasing down the columns. And for this, we only need the order index. Okay. So, for instance, this makes it possible, for instance, to give a meaning to something like this. These are the variables which are indexed not by the set of natural numbers, by the set of all integers. For instance, we can use even the as the index set, we can use the set of rational numbers or what we want. The only thing which we really need is the total order. Okay? Now, I would like to state the result, which is called the Cauchy identity. Which is probably the most important identity in the theory of symmetric functions. The formulation looks as follows. First, I would like to write it, and then I will explain its meaning. Take the sum over all partitions or Young diagrams, and take X and Y are two alphabet arbitrary, and take this sum, and the result is the product over small x's ranging over this alphabet and the letters over the second alphabet, and the product is like this. Or if you wish, we can write it in something like this. This is actually, it's the same. Then we have to take the product over i's and j from 1 to infinity, a double product. This is the same. This is just the same. The question is how to understand this. How to understand this. First of all, we have to stress that the left-hand side is not excuse me. You have to understand in what algebra this object lie. It is not the left-hand side and the right-hand side are not elements of this algebra. Why? Because in the algebra of symmetric functions, all objects, all elements are elements of bounded degree by the very definition. But here, there is no restriction on the degree. So how to understand this equality? There are several possibilities which are equivalent. So how to understand? How to understand? One possibility is to work in the algebra of all power series in the x variables and y variables without boundedness restriction. This is one option. Another option is to introduce an auxiliary variable there at t and introduce this t into this formula. This can be done as follows. And introduce it as follows. For instance, one can write t to the number of boxes, the size of our diagram, and then you get these things, which means that now we can place the both sides into the algebra tensor sim and tensor, say, the algebra of formal power series in the variable t. Or we can imagine that we take this ring as an extension of the base field Q. Or, for instance, we can introduce t inside one of these functions, that is to write the same equality as follows. And we get the same. So these are possible ways to interpret this equality. So this is called the Cauchy identity or Cauchy formula. How to prove this? Proof. First of all, let me formulate very simple but important principle. Of a very general nature. It can be stated as follows: to show something, verify some identity in symmetric functions, it suffices to check it for symmetric polynomials. That is to keep only finitely many variables, and all the extra variables can be set equal to 0. Okay? By the very definition of the algebra of symmetric functions as a projective limit. From this
very definition, it follows that we can use this principle. So let's follow it. So what we obtain? So it suffices to prove. One can say some truncated version of a Cauchy identity. Truncated version is as follows. So again, we keep only n variables. N can be arbitrary. But then you have a sum over this set of partitions only, because otherwise we get 0. And on the right, you have the product from a finite product now. Okay. So we have reduced the Cauchy identity to this one. Okay. What next? Next, we just use the definition of the short polynomials as a ratio of two determinants and write it as follows. Sorry. So we set L sub I as before. And we replace the sum over Young diagrams. We replace the sum by the sum over all n tuples of integers, satisfying these inequalities. Okay. And what we get? One determinant. And the equality that we want to get is, it should be equal to the van der Monde in the x's, the van der Monde in the i's, and divided by this product. Here I call it x is this collection of variables, and y is this collection of variables. I just rewrote this equality. I represented each of these polynomials as a ratio of this determinant divided by this determinant, and then I transferred the denominator to the right-hand side. Okay? Now, what next? Just look at these expressions. Look at these expressions, and the idea is follows. The idea is follows. Consider two matrices. Two matrices
introduce two matrices A and B of size n times infinity and infinity times n. So A is a matrix with infinitely many columns and n rows, and the columns are indexed in the reverse order by the numbers. And this is A, and this is B, and here we have just a moment. No, so we have to assume this is a bit unusual. Maybe I will erase this, because the numbers go from right to left. Okay? And here, sorry, and here the rows go from up in this direction. And the entries are, here are X, J, L. I'm sorry, maybe we have to add 0. So the numbering starts with 0. And the entries here are, okay. And look at this. So what we have, you take some minor, which corresponds to a given collection of these numbers. Maybe we have to read, no, it's okay. Just we read them just in this way. And here we have a similar minor, which is this one. And we have to take the sum over all possible minors of size n. And then we apply the Binet-Cauchy formula.
Sorry.
Yes.
In the right diagram, the entries should be Y, K, L, I think.
Yes, you are right. You are right. Thank you very much. Indeed. You are right. Thank you. Right. So we apply the Binet-Cauchy formula, which says us that the sum of minors equals the determinant of a product. Okay. So we have to take the product of these matrices, okay, and take its determinant, and this gives us the determinant of size n by n this is because because it's just the product L this reason. Okay. So now our identity is reduced to the following. Okay. So this is the so-called Cauchy determinant. And probably we know how to prove it, how to prove this. And this is a fact from elementary algebra. One possible proof, which uses some idea, some general and useful idea, is as follows. So proof of a Cauchy determinant formula is as follows. Just multiply the both sides by this expression. So multiply both sides by the denominator. For instance, we can do it as follows. That's all we get. So this is reduced to the following. And what we get on the left-hand side, we have a matrix with all entries. All entries here are polynomials because this denominator is cancelled with some factor in the numerator. And what is the degree? The degree of this polynomial is equal to n minus 1. So the total degree of the left-hand side is n times n minus 1. And this is exactly the degree of the polynomial on the right-hand side. Equals the degree of the right-hand side. So we have some identity to be proved for polynomials of the same degree. Next, the polynomial on the left-hand side vanishes if two x's or two y's are equal. Okay, this is easy to see because two rows become equal or two columns become equal. And this means that it can be divided by the Vandermonde in the x's and the Vandermonde in the y's. And because the degree is the same, they should be equal up to some number factor. And finally, we need, so this means left-hand side is equal to the right-hand side times some factor. Some factor. And finally, we need to prove, we need to prove that C equal to 1. And again, the trick is very general. Just compare the higher degree term with respect to the lexicographic order. On the left, you get, on the right, compare top degree monomials. Top degree monomials. On the right-hand side, we have this one. And what we only need is to check that the top degree term on the left is exactly this one. So this is the end of the proof. Okay. Maybe some questions? Please ask if something is not clear. Okay. What next? I would like to slightly rewrite the Cauchy identity in the following form.
Sorry.
That's okay.
Go back to the product above in this page. I want to ask the subscript is
what
the product above.
This one?
Yeah. This product is sorry, below. No. Page 6.
I don't understand. Where to move? Up or down?
Next page. Next page.
This one. This one?
No. Next page.
Next page. This one?
Yeah. In the denominator, the subscript is ij equals 1 to n. It's jk. Sorry. Is it?
I don't understand. Excuse me.
The product label and is from is it from jk to n? You write k equals 1 to n and I and j 等于equals n equals e from e to n.
I don't understand. Sorry. What product?
We have the same index in determinants, k. Yes, we have k in the product and we have k as the index in matrix.
I see. You are right. Excuse me. You are completely right. Thank you. This is a bad notation. I understand now. Thank you very much. Okay, now it's clear? It's okay now?
Thank you.
Thank you. Okay, so what next? I would like just to slightly rewrite the truncated form of the Cauchy identity as follows. So assume we have m axis, that is m, and n y's, and take the same form of identities. Now we get I ranges from 1 to m, j ranges from 1 to n. And what here? What we have to put here? And then we have to put here the sum over lambdas such that L of lambda is at most the minimum from these two numbers. So this is easy to understand, just because if you have a Young diagram lambda and some collection of variables, if this collection of variables is too small with respect to the length of lambda, then the Schur polynomial, the corresponding Schur polynomial vanishes. So this is trivial, but it's useful to keep this in mind. Okay, so now I want to introduce the H functions, which are called complete homogeneous symmetric functions. So H is from homogeneous. So the definition is as follows. Definition. H sub n is a symmetric function, an element of this algebra, which is defined as follows. H sub n is by definition the sum of all monomial symmetric functions of degree equal to n. This is why it is called complete, or which is the same, the sum of all monomials of total degree n, which is equal to pi. We agree, this is some kind of agreement that h sub 0 is equal to 1. Equal to 1. What I would like to say, this is equivalent if you have some set, some ordered set of variables, then we can write this definition as follows. The sum over all indices This is a simple exercise to verify that this agrees with the initial definition. Also, it's easy to get a generating series. I write here in my notation of some alphabet. multiply by a formal variable. Okay, and what we get is an infinite product of these letters. Letters are some variables, or if we wish, we can write the same in this notation. So this is a generating series. And both sides are can be viewed are in the algebra. One can say we add formal power series in T. Okay. So please keep it in mind, the generating series. And as a first corollary of the Cauchy identity, we get the following: H sub n is equal to the Schur symmetric function, which is indexed by one row Young diagram, which means that is the Schur symmetric functions indexed by this partition, which corresponds to the Young diagram with one row and boxes here and columns. And how to prove this? But this is trivial. Just look at this formula. Okay. So maybe I have to denote it by 2 stars. Proof. Just look at this formula. Substitute. M can be arbitrary, but n equal to 1. And we get on left-hand side, we get a sum over lambdas with, but these lambdas are exactly of this form. And then use and compare the result with the generating series. After this, we easily get the claim. Okay. This is an easy proof. And if you want to use the initial definition of the Schur polynomial, so what this means? This means as following. A direct proof would be not so evident. So so assume that we have some m variables, so we have to prove that how to prove this? You had to prove something like this. Take the determinant and put here x1 to the power n plus m. Here. And divide by the van der Monde. And why is it equal to the right-hand side? Okay, it's not evident. But this modulo the Cauchy identity, the proof is trivial. Okay? Now I would like the next result that I would like to prove. It is called the Jacobi Jacobi-Trudi identity or Jacobi-Trudi formula. It says the following. A sure function indexed by some partition lambda can be written as the determinant expressed through the h functions. First of all, I have to explain what exactly this means. So, first of all, I recall that h0 is equal to 1. Next, by agreement, we assume that the h functions with strictly negative indices are equal to 0. And because of this definition, look at this matrix. Look at this matrix. I claim that this matrix has the following form. In principle, it is an infinite matrix. The matrix on the right-hand side is infinite, but almost uni-upper, unitriangular, which means that you have some block, some finite block of some size, at most of a size, the length of lambda. And next we have ones, and here we have something, and below we have zeros. And this matrix is of infinite size, but its determinant is well defined because we can truncate it at any level which is at least equal to this number. And the result is the same. The determinant becomes stable as we truncate it on the level which is greater or equal to this number. So this makes sense. Or if you wish, or can write n, provided that n is greater or equal to L of lambda. Okay. So this is the claim. This is the claim, and how to prove it? How to prove it? Proof. So take n large enough. So suffices to take of this size. And write the Cauchy identity. Write the Cauchy identity. And the idea is as follows. We want get some information about this object, but we regard the left-hand side as a, or maybe it's better to say, better to say this, is a generating series for this object, So we regard these objects as formal variables. Okay, so in the simplest case of one variables, we get this. Okay, so the role of T here is played by the whole Schur polynomials in the Y variables. And next, the idea as follows. This is an important principle, important general principle. So assume that we have some series. No, sorry, not so. So assume that we have some symmetric polynomial. And expand it in Schur polynomials. So we can expand it. We can expand F in Schur polynomials. And according to our notation, I will write as follows. F is equal to some linear combination in the Schur polynomials in the variables y's. And we want to extract, how to extract the coefficient, some coefficient, okay? How to extract it? The recipe is follows. The recipe is equal. I will write it first and next I will explain. what is written here? In general, the general notation in combinatorics is as follows. A notation like this means that we want to extract some coefficient, which is written here, the coefficient, say, of some monomial, and this monomial is written here in some expression, and the expression is equal here. Okay, so this is read as follows. We want to extract the coefficient of such a monomial from this expression. As usual, I assume that Li and why? Why? This is because we apply the very definition. We rewrite this as follows. F multiplied by the Vandermonde is equal to the sum of lambdas, some coefficients, unknown coefficients, and then we have the determinant and now it becomes clear, I hope, that the coefficient that we want, this one, is just the coefficient of this monomial because it comes from the expansion of this determinant. Okay. Some questions maybe? Is it clear or not? Okay, so I hope it's clear. But now apply this to our apply. So apply. So apply this principle to our identity. And here, C sub lambda is not a number, but the whole sure function. But it's not important because we can work in any algebra of coefficients. So applying our principle to this formula, we get C sub lambda, which is equal. No, I can just write. Okay. Is equal to a coefficient in what? Product over and multiplied by the Vandermonde Now look, please look at this expression here and rewrite it. Rewrite it as follows. I reproduce the same coefficient. But I write this expression as follows. I have to explain this. So what is h of y? This is the generating function, generating series for the hn of x. Okay. One could write it in more detailed notation as follows. So the trick is to eliminate the x's. Just write the x's are hidden here, are hidden in this notation. Okay. So we regard this double product. This is a double product. When one y is fixed, we get from this the product of such a type. So it is a generating series for the x variables. Okay. Now look at this expression and recall that this is a van der Monde determinant. So this can be written as follows. We take again a coefficient. From what? We take the determinant, the van der Monde determinant, which is and multiply it by this expression. Is it clear? I just wrote the definition of the van der Monde determinant without this factor, and then I introduce these factors inside the determinant. Okay. Now I just expand the determinant here. We get the sum over all permutations, sigma, from the symmetric group in n letters. We put here the sign of our permutations and write and multiply it by this times multiplied by this, and so on up to number n. and multiplied by this. And what next? We want to extract this coefficient. But how to extract it? We have to get this variable from this term, and so on. This variable from this term. Okay? And to get it, so to get the coefficient of our monomial, we obtain the sum over n. Here we have and here we have to put the coefficient of the coefficient in and like that. Sorry. We don't need this. But what it is? Maybe it's better to write it. Okay. I want only to say that the coefficient okay. And so the factor here is equal to which is equal to so we get the sum sorry And this is exactly our determinant. Okay. So I recall what we need to memorize actually is this general principle. To extract this coefficient, just multiply this polynomial by the van der Monde and try to extract the coefficient of monomial, and applying this to the Cauchy identity after some manipulation with determinant, expansions, and so on, we get the desired result. Maybe some questions? I have not so much of time. Okay, I will try to begin maybe. Try to begin. The next topic is the coproduct. Coproduct in the algebra of symmetric functions. So what is a coproduct? So assume that we have some algebra. By coproduct we mean some map from our algebra to the product of two copies of this algebra. And usually we assume that some extra conditions are satisfied by, I don't want to mention them at the moment. I would like just to introduce, this is usually denoted by delta. I would like just to introduce this map for the algebra of symmetric function. The idea is as follows. So assume A is equal to the algebra of symmetric functions, and we want to construct a map how to do that. The idea is split an alphabet x, which is infinite. It is infinite. We need an infinite alphabet in order to deal with say Schur symmetric functions of arbitrary size, indexed by a partition of arbitrary size, and split it into two infinite parts. So write X as a disjoint union of two sets, which are both infinite, two alphabets. Sorry. And take an element f, symmetric function. So it is a function in two sets of variables. And because f is symmetric, it is separately symmetric in the y variables and symmetric in z variables. And from this, it follows that as such an object, it belongs to the tensor product of two copies of symmetric functions. Okay? So we get some map. It is called the coproduct of symmetric functions. What next? So we apply it to our basis. Take our basis. Our basis. And apply it to the Schur function. We get some element from this. And here we have a basis. Here we have a basis formed by tensor product of two Schur functions. So we can write, we can expand and get some coefficient. For some reason, I will denote it as follows. And the sum is finite. Sum is finite because it is in fact restricted. It is in fact restricted to pairs of partitions such that the sum of sizes is equal to this one. Why? This is because our map is consistent with the grading. The degree on the right, if you take a homogeneous element, and this is a homogeneous element, its image on the right-hand side should also be homogeneous and on the same degree. And this gives us this restriction. So the sum is finite. On the other hand, so these are structure coefficients of coproduct. But on the other hand, you have a usual product map because our algebra of symmetric function has a usual multiplication. So write the multiplication through. The multiplication, the product. And write the structure constant of the product, which means that we multiply one function by another Schur function, and we get, and we can expand the result in the same basis of Schur functions. And here again, actually, in fact, the sum is over lambdas such that, again, because the product is compatible with the grading. The theorem which I will prove in the next lecture is as follows. These coefficients are the same. And they are called the Littlewood Richardson coefficients, or LR coefficient for short. So this will be our next goal, to prove this remarkable identity. Okay, that's all for today. Maybe some questions? Okay, I will send you very soon, maybe today or tomorrow in the morning, a letter with some problems and some links. So please check your mail, and if you don't find my letter, please check the spam box. Maybe it will be sent to it will be in the spam box, as sometimes happens. Okay. So thank you. I switch off the recording.